It's that time of year again, back to school, which means we've got fresh classes starting in the machine shop. And with any new class, usually, how we go about this is we hand out our textbooks. And chapter 1 is shop safety. Chapter 2 is usually getting into measuring. And a rite of passage for any machinist in the measuring world is learning how to read one of these things, a vernier scale. So hopefully in this video, we're going to clarify some things about how to read verniers, how they work. That way we can get your students past this part of their machining career so they can get on to the fun stuff of actually making parts and using digital measuring devices instead of this thing. So as we start digging into this vernier, this measuring device, I'm going to be working a lot in Mastercam. And if you're interested in using this file to play around with on your own, there'll be a link below here in the blog to download and have a look if you want to. So that being said, let's dive into this vernier and talk about what it is and how to use it. So usually the way the classroom discussion starts about vernier is a discussion on where it came from and who invented it. And instead of reading that from a textbook, I'm going to get some help here from the ever knowledgeable ChatGPT, and let's find out what a vernier is and some history about it. What's a vernier and who invented it?
A vernier is a type of secondary scale used to allow for more precise readings on measuring instruments like calipers and some types of scientific equipment. The idea is that it helps you measure something more accurately by using this additional sliding scale to read between the lines of the main scale. As for who invented it, it was created by Pierre Vernier, a French mathematician and instrument inventor back in the early 1600s. His invention has been super useful for anyone who needs to measure things with fine precision ever since.
So that's a good bird's eye view of what a vernier is, and let's now dig in a little bit deeper with this model that we have up on screen. So they talked about a main scale and a sliding scale, and our main scale is these two. We actually have two main scales on this example here. We have one here from 0 to 150, and that's in metric, and then we have one above it that goes from 0 to 6 inches. So we have two main scales, and we also have two vernier scales. So this scale down here, this is the vernier scale. It does slide, which we'll show in a minute. This scale down here is only relevant to this metric side of the scale. And the top side over here, that is the vernier scale for the inch side of the vernier. And as you would expect, this portion of the caliper that contains the vernier scales, it does slide, and that's what produces our measurement and our vernier scale reading. So let me just clear out of this, and we'll zoom in on the current measurement on the vernier. So you can see, we'll look at the metric side here. We're looking at where this 0 is. And you can see that we are roughly just past, this would be 50, this would be 55, 56, 57, 58, and we are just past 58. So the vernier scale is then where we figure out how far past 58 we actually are. If we were to zoom in, and maybe you could take a guess at how far past we are, you could say maybe that's 0.1 past 58, but without a device that actually notes where the measurement is, it's kind of not a great way to measure things by guessing where something is. So the vernier scale is used now, and this is where we would look for where the next line matches up. And I'm fast forwarding a little bit here, and we'll talk more about this in a second. But currently the number 2 lines up with the line above it. So that means we would be 58 millimeters, and then whatever this number 2 represents, if we zoom out, we can see the scale here is 0.05 millimeters for each deviation. So this first line would be 0.05, this next one would be 0.1, 0.15, and then 0.2. So our measurement is actually 58.2 millimeters. And we had guessed initially 58.1, so if we needed to be precise in our measurements, our guess would have been out by 0.1 millimeters. So let's dig in now a little bit deeper on how to read these scales, and while we do that, let's bring our trusty assistant back here and ask a few questions and see if they can clarify how the scale works and how its measurements are actually read. How do I read a vernier scale, and how do I make a vernier scale?
Absolutely. Reading a vernier scale might seem a bit tricky at first, but once you get the hang of it, it's pretty straightforward. So when you're reading a vernier scale, you start by looking at the main scale and noting down the measurement just before the 0 mark of the vernier scale. That gives you the main reading. Then you look along the vernier scale to find the line that lines up exactly with any line on the main scale. The number on the vernier scale at that alignment point is the extra fraction that you add to the main reading, giving you a more precise measurement. As for making a vernier scale, it's all about creating that second scale with a slight offset. Typically, the vernier scale is just a little shorter and divided into one more division than a certain length on the main scale. For instance, if you have 10 divisions on your main scale and a certain length, you might divide that same length into 11 divisions on the vernier scale. This way, as you slide it along, one line on the vernier will align with the line in the main scale at each fraction of a unit. In practice, most people just buy calipers or measuring tools that have a vernier scale built in, but if you're really into it, you can make one by carefully marking out those divisions yourself.
Okay, so again, AI is getting us partway there, and I think it gave us a little bit of wrong information, and let's talk about that. So a few things it talked about there was reading it and finding the line that lines up. So number one, that can be difficult. I just happen to know that the number 2 lines up over here, and I was easily able to derive that. But as we make a scale, I'll explain more on how to read it and how to quickly find out or be able to tell which line it is that lines up. But when it talked about making a vernier, it talked about that there's more numbers on the bottom scale than the top, which is actually reversed. So let me close these scales over here. Let me grab this thing over here, and we're gonna move this from here, and we're gonna go and close our scales right down. Okay, and it talked about there being more or less deviations on the main versus the vernier scale. So if we look at this scale, we can see in the top we've got, in the bottom, both our zeros are lined up. And then all the way over at the end, our 10 is lined up with number 39. So what ChatGPT mentioned there being one less or one more, we've got 39 divisions on one scale and 10 on the other, so that makes no sense. So we'll come back to this and explain what's going on. But to start with, we're going to go and create a vernier scale from scratch, and we'll see how these actually work. So let's start over on a blank level over here, and it's going to create a piece of wireframe geometry that is a straight line, and let's make it 1 inch long. Okay, and then we're going to make some spacing between our lines. We're going to make some lines here. I'm just going to translate them over. And let's do 10. And I'm just going to use 1 inch. It's just a round number. Well, this could be 1 inch, it could be 1 millimeter, it could be a cob of corn. It doesn't matter. Wherever the deviation doesn't matter, just as long as they're consistent values. Okay, and to make this look like an actual scale, let's draw a little line down here. And so we've got, there's number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so we've got 10 equally spaced lines. I'm going to number these, and I'm going to do this quickly with some movie magic. And there is our completed scales, numbers 0 through 10. Now we need to make the bottom scale. So this is going to be our main scale. Now we need to make the vernier scale. And this is where ChatGPT led us astray a little bit. And this is where something like a legit article is sometimes useful. So back on our Wikipedia, if we scroll down here, we can get some information about the function of a vernier scale, how it works. And this is what we're after down here. And to save reading the entire paragraph, I'll just highlight the important part, and that's right here that says, such that the length of n-1 main scale divisions is equal to n vernier scale divisions. Okay, so in short, whatever we want to be able to measure accuracy, let's say we're going to measure our vernier scale, we want to divide this into 10 equal parts. If I have 10 vernier scale divisions, it has to fit into n-1 main scale divisions, so n being the vernier scale divisions, which will be 10. 10 minus 1 is 9. So my 10 vernier scale divisions needs to fit in to 9 main scale deviations. So with that, we've got the, I've got a 0 line created in here for our vernier scale, and I'm just going to do a translate on that one. And as mentioned, we need to move it, but last time we did a straight 1 inch movement, and obviously we don't want to do the exact same thing as we did at the above scale. This would never make a reading for us. So these 10 lines need to fit within this distance right here, which since we're working with inches, I know this is 9 inches, so I can switch this over to total, and this would be 9 inches. Okay, let me click OK. So there I have, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 equally spaced divisions that fit within 9 main scale divisions. So a bit more movie magic here. I'm going to number these guys on the bottom over here. And there's our vernier scale all populated with values. Okay, so let's go ahead and move our vernier scale now. I'm going to move this by a known value. I'm going to move it 400 thou to the right. And let's go now and figure out how we can read this scale a little bit better. So there we can see our 0. It has moved past our 0. And again, it's hard to tell where this is. Is it halfway? Is it less than half? It's obviously less than halfway, but we can't tell how far it's moved just by simply looking at this 0. Now, again, we need to look for the line that does line up. And since we do know that we moved it 400 thou, so the 4 is the line that's going to match up. Notice what the lines look like around the 4. So notice this line is well to the right here. This one's to the right. This one's to the right. Obviously, this one's lined up. Then all of a sudden over here, we got lines that are to the left, and to the left. So when you're looking at your vernier scale, especially when you get into finer measurements, it gets hard to read. You're looking for this type of motion to switch from the line being on the right to all of a sudden the line being on the left. And usually it's going to be the line in between where it starts to line up. Okay, so where this can become an issue is if we have, a scale that can read 0.1, but if we start moving that scale into finer distances, let's say about there. Okay, so now none of the lines line up here. Okay, so none of these lines will line up. So which is the line that's closest to lining up? This is where you're looking for where it transitions between being on the left to being on the right. So it's somewhere in between these two. So the exact measurement is finer than this scale can measure. So we can't accurately make a measurement, but we know it's somewhere between the 3 and the 4. This one's to the left, this one's to the right, and this one's to the left. If we hop back to our main vernier, and let's maybe move this again. Let's do a translate, and we'll move this thing over. Let's say about there. Okay, so if we want to read the bottom scale, we'll stick with the metric. So we can see we are past 40. Let me just turn this highlight off for a minute. It's kind of annoying. Okay, so we're past 40. We're past 42. It's 42 in a bit. But which one? Let's get this whole scale on screen. So we can see obviously like the number 2, the 2 is to the right of the line here. The 3 is still to the right. If we look over here at the 7's on the left-hand side. This one's still on the left. The 6 is still slightly on the left. 5 is on the right. So I gotta say it's probably this one right here that's lining up. Again, let's use our Superman vision here and really zoom in. The 5 is to the right of this notch. The 6 is to the left of this notch. So even though this one isn't perfectly lined up, our reading would be, I would be giving it this one right here. So that would be 42.55 millimeters. And that's as accurate as we could measure given this tool. Obviously, that's a little bit different measurement, but you can only measure as accurate as your tool is capable. And that would be the measurement for this vernier. So let's go back to our homemade scale for a minute. And we've been looking at basically things that all have multiples of 10s, which makes things nice and round. Could we make a vernier that's not a multiple of 10? And let's show how we can do that real quick. Let's just select these lines. And actually, I'm going to keep some numbers here. I'm going to get rid of all that stuff. And I'm going to get rid of these lines. I'm going to use these numbers again. So what do we want to do? Say quarters. We want to divide this thing into quarters. So we know quarters, there would be 4. So we would need, if we wanted 4 lines or 4 deviations on our vernier scale, those 4 lines would need to fit into 3 deviations of the main scale. So let's take this line, and we're going to translate this. I'm going to do a copy, and I just need something in here so I can do a total distance of 3 inches, and I want 4. Okay, so our vernier scale is going to have 4 lines within the 3 deviations of the main scale. And let me just, so when I made these with, I used the drafting note instead of the wireframe create text. So this allows you to go back into the note and either edit it or reposition it. That's a nice little tip for Mastercam users. Okay, and there's our new vernier scale that's set up to do basically measurements of quarter. So I guess this shouldn't be 1, 2, 3, 4. This should be 1/4, right? And this should be half. This one should be 3/4. And then this would be just the number 1 again. Okay, and to see how this works, let's grab this and let's do a translate. And if we move this 1/4 inch, notice which line lines up. So this line here is to the right of this guy. This line here is to the left of this guy. This one obviously lines up. And there we've got our vernier scale that measures quarter of an inch. Or 1/4 inch increments is the better way to say that. So to kind of come full circle back to talking about this scale down here and the number of increments on it versus the scale that it lines up to, I'm going to bring up some other scales here. Here's a typical inch vernier scale. So I've got 0 to 1 inch and up to 2 inches. And the bottom scale is cut up into 25 deviations. So these are 25 increments here, and our main lines here are 25 as well. So basically what this means is this scale can measure 0.001 of an inch, or 1 thou. And as we can see, we've got 25 deviations on the vernier scale. And that lines up to the number 6, which if each one of these has 4 spaces, 6 times 4 is 24. So 24 deviations on the main scale is 25 deviations of the vernier scale, and that will allow us to measure 0.001. But again, even this, I have a vernier around here somewhere. Is not the scale you're going to see on this guy. It's going to have a different scale. More likely what your inch scale will look like is this one over here. You're going to see 0 to 25, and it's probably going to line up with what we'll call is the first notch past 2, or that would be 1.225 inches. And if you were to count all these deviations, there's a lot more than 24 there. So what is going on with these two scales, and how does this vernier scale work any differently? So what some manufacturers will do is to make the scale a little bit easier to read, especially when we're dealing with very, very fine numbers, is if we were to take this scale and add in a line exactly in between them, and place one of these at each spot, what this scale could in fact measure would be half a thou, but half a thou on a vernier is not ideal. But if you were to then count up all the notches down here, we would in fact have 50. And this top scale here, this would be, if each one of these is 4, this would be 40, 44, 48, 49. We would have 50 notches within 49 main scale divisions. Just that they leave out those half thou deviations. Okay, so the scale still works exactly the same way. Bottom scale has one more number than the top scale, but we just happen to leave out the very, very small increments, which would be almost impossible to read. And that's the exact same thing that's happening on this scale over here. Let's zoom in, and let me turn this highlighting back off again. If we were to add a line here, so that each one of these was 4, that would make 40 total lines down here, fitting into 39 deviations on the main scale. Just that we leave those notches out because it's too fine of a measurement to be able to discern what actually lines up. So that's basically what's going on and why the numbers don't make sense as far as that normal n-1 formula. But those lines are there, they're just hidden, so you can actually read the scales. Okay, so whenever you look through this file here, there's a couple of different scales I've got up here. There's the scale one of inch, and it's laid out exactly like you would expect, 25 and 24. The next one's laid out more than likely what your actual vernier would look like in the shop, 25 with half of the numbers missing. There's also the metric scale over here, and then of course the vernier you can play with as well. And I'll leave this demo in here as well that you can play around with and adjust if you're looking for something to do on a Friday night and verniers are on your mind. So with that, let's bring back our our trusty assistant here and see if they have any final parting words on verniers and such. What's a fun fact about a vernier scale?
Sure. A fun little fact is that the vernier scale is sometimes called a nonius, which comes from the Latinized name of the Portuguese mathematician Pedro Nunes. He was an earlier scholar who worked on similar principles before Pierre Vernier. So in some older texts or certain languages, you might hear it called a nonius scale instead of a vernier scale. It's like a little nod to the history of precision measurement.
Well, that indeed was a fun fact.